You did shops.
All right, guys. So today we're going to get into series circuits. We kind of touched base on the concepts. Yes, Andrew?
Before we start, I just want to point out that we've been working with series circuits in the lab, and we're now just learning about them.
You've not just been learning about series circuits, you've been dealing with parallel circuits and composition circuits and a bunch of other stuff. But yeah, now we're going to talk more about the math. We're going to look at them a little bit deeper.
Okay.
And you're 100% right.
Because that's like really confusing.
You know, in my experience, it's very hard to learn anything when you don't have the basis of what you're talking about. So having your hands on it for a while and being familiar with what they look like will only support you in being able to take a look at the mathematics behind them and do basic calculations. But the idea is, you know, we don't want to overload you guys too hard, too fast. Keep it progressive, teach you the foundations, have a really strong foundation so that when you guys start to do more and more complex things, you can always break it down to those root blocks that you've been learning for a long time. Does that make sense?
Yeah.
Cool. So we're going to talk about series circuits. Let's just kind of jump into it then. So this guy over here, his name is Gustav Robert Kirchhoff, and he is the guy who invented Kirchhoff's law. So today we're going to be going over how to identify a series circuit. I think you guys can do that pretty easily. Determine the current within a series circuit. We'll do the same thing for total resistance. How to apply Ohm's law in a series circuit, which I think you guys can do pretty well, but maybe break it down into like the little puzzles that you can solve. Then we'll talk about the total effect of voltage in a series and how to apply Kirchhoff's law to that. So over here we have one giant series of resistor after resistor after resistor. According to Kirchhoff's law, if you wanted to know the total resistance of all of these resistors, you would simply add them all up.
Yeah.
So one pathway, we can kind of see here, this is a simple path, it's easy to follow, but the end of one always leads into the beginning of the next one. In the second example, we have 3 resistors and it goes in a more funky pathway, and then it just gets more and more funky, more and more turns. But regardless of the shape that you wire them all down, there is no point where one resistor is connected to 2 through the same branch. So it's always one exit, one entrance, one exit, one entrance, all the way down to the most kind of twisty-turvy one on the bottom right there. So that pathway from A to B is one continuous path. That's what we're talking about when we're talking about a series circuit. Now, if we want to add up all of the resistances, it basically says the total resistance is equal to the sum of all of the resistances in the straight. So if we have 3 resistors here, you add up the resistance of resistor 1 plus resistor 2 plus resistor 3, and that'll give you the total resistance. Now, here is an example that we'll do together. So if we have this circuit here, we have source voltage 18 volts, irrelevant for this example, but then we have resistor 1 with 1 kilo ohm, resistor 2 with 2.2 kilo ohms, and resistor 3 with 2.7 kilo ohms. Who can tell me the formula we would use to get the total resistance?
1 plus R2 plus R3. Exactly.
R1 plus R2 plus R3, exactly. And who can tell me what that number will actually give us? 5.9, let's check that out. 5.9, really good job. Here's another example. We have the same situation here. And so who can tell me the formula for this one? Someone from this side of the room. Theo. R1 plus R2 plus R3. There's a 4th resistor here?
There is, but it doesn't have that.
All right, so plus R4. Yeah. So always, that's one really important thing to notice. Sometimes people make mistakes or they don't, and they do it intentionally to kind of like throw you off a little bit. But you should always pay really close attention to the actual circuit. So if you see a resistor on the bottom, whether or not it says resistor 4, you can go through, see 1, 2, 3, that must be 4, right? Always pay attention to the components, not necessarily the labels. It'll help you very much. And I know when we were doing some of the labs, we did the same concept where there's a picture that doesn't have a switch in it, but the actual schematic has a single pull, single throw switch in it. And I'll tell you, like half of the people who do that first lab always build it according to the picture. And the lesson is, don't trust pictures, trust schematics. The schematic, learn to read it, and it's 100% faithful, where, especially when it gets into very complicated circuitry, you're not gonna be able to follow a picture unless it's like the most neat, beautifully laid out circuit on the planet. The same idea is true for pretty much all things. So try to like focus on the parts, not the labels, if that makes sense. And I guess we already got that. Yeah, okay, so who wants to tell me the final answer for these 4 resistors? 2 mega ohms. We got 2 mega ohms. Really good. Okay, and one last example. I think you guys got the hang of this. Now there's 5 resistors. We add up all of the 5 resistors, and we end up with 3 giga ohms. So now that we've talked about resistance, how to get the total resistance, the next thing to do is we want to talk about voltage. So this is where I was saying the sum of all voltage drops is equal to 0. Or the way that they usually say it for like more practically is voltage source is equal to the voltage of resistor 1 plus the voltage of resistor 2, all of the components within the circuit. So we'll get there in about 2 seconds. So you can see here there is a closed loop system, and it is specific to closed loop systems. You have the battery over here. So you can imagine if the battery is like 24 volts, and all 3 of these have the same resistance, and we'll get into this in the second slideshow that we're doing today. The breakdown, if all of them have the same resistance, will be equal between the 3 of them for the voltage drop. So we'll have 24 volts here, 8 volts on this drop, 8 volts on this drop, 8 volts on this drop. And so you'll have 8, 16, 24, and then when we add up the segment for voltage source, it'll be negative 24 because it's adding 24 volts into the system, which will give us our 0, right? So the other way to say that is voltage source minus voltage of relay 1, resistor 1 plus resistor voltage of resistor minus the voltage of resistor 2 minus the voltage of resistor 3 until n resistors or components that have some resistance will equal 0. Now here's a practical example for that. Who wants to help me figure out the formula for the voltage source? Yeah, you guys got it. So if we take the voltage of the first resistor plus the voltage of the second resistor plus the voltage of the third resistor up to Rn, so we have 5 resistors here. We're going to get the voltage source. Who can chug that out? Chug that math out for me. It's really important, guys. Like, grab your calculators and run these numbers. It's easy, free practice where you can test it out in an environment that if you try it out and you have a problem, I'm right here to help you guys after class or possibly even during class, depending on the question. I'll let you use your judgment whether it's a question that should be asked privately or not. Andrew.
In theory, could you just use Ohm's law to find the voltage?
You could, but that's not the assignment. We're using Kirchhoff's law. Yes?
6 kilovolts.
6 kilovolts? That sounds reasonable. Let's find out. No, it doesn't say. It's probably reasonable. So one thing you're going to notice here is that there's some of these with really large resistances, which is like the 2.57 giga ohms. And there's some with a really small resistance, like 700 ohms. And this 5.14 kilovolts is a majority of the voltage, right? So you might end up seeing, if you see 1400 microvolts next to 5.14 kilovolts, it's like a factor of 10 to the 12 apart from each other. You're not even gonna see that affect the value. But these bigger voltages like 854 volts, maybe the 5 volts, and even when we get to millivolts, it's already very far away. Like, we're just talking about a thousandth of a decimal place for the other values there. So it's just interesting whenever you're running numbers, it's so incredibly valuable to mentally be able to aim the trajectory of the approximate answer. And that way, if you do like your computations and you find out it's something that was really, really far off from the ballpark you thought the answer should land, it gives you a good idea to turn away and be like, I need to figure out what went wrong here. Where in your example, you told us it's 6 kilovolts, and that 5.14 kilovolts plus 0.85 kilovolts is very, very close to 6 kilovolts. So that makes perfect sense, right? That's the example where you're like, okay, I can feel good about my answer. Yeah? How about this one here? Who can do it next? Sorry, this is the same question. All right, okay, so we're just breaking this down. So yeah, we have all the 5 resistances, 5 voltages, we add them all up, and after we add them all up, 6 kilovolts on the dot, and that's gonna be 6E3. Does anyone know what the E on your calculator does for those who have an E and 10 to the power of 3? Yeah.
Oh, just for scientific notation.
It could be scientific notation. It could also be something else.
Is it exponent?
It's pretty much exponent. So E literally stands for 10 to the power of blank. So if you were to put, 2.34 E6 into your calculator, if your calculator only uses E and not 10 to the X, that would give you 2.54, I forget what number I actually said, times 10 to the power of 6, right? Because E6. Okay? Cool. Now, we're going to talk about conventional flow versus electron flow, which, honestly, it's a very interesting story that I feel like most of you guys have heard already. But back in the day, Benjamin Franklin started the concept of electric flowing from the positive to the negative. Mm-hmm. And then years and years later, a British physicist named Joseph John Thomson discovered that the electron's the one that actually moves around. But because so many people already were on doing all the mathematics based on conventional current, or from the positive to the negative, it just kind of stuck around. But we know better. They don't want to change all of the math over. Okay, so for a series circuit, all of the current entering any point is the same as the current leaving that point, which means realistically in every series circuit, the current is always the same no matter what. You can kind of think about it like if each resistor puts on a certain amount of if the flow is going like a certain speed and you have a bunch of resistors, and those resistors all add like a little bit of slowness to that speed, it kind of takes all of it and just uniformly presses at the speed that works for all of them, right? It doesn't go in and give you a quick bout and then a slow bout and then like a really fast one again. No, it finds that magical speed that all of the electrons can flow through everything. Does that make sense? Andrew, you're smiling. What's going on? No? All right, what's going on?
Yes, I have a question. So for example, if we have a light bulb before the resistors, it'll still the current will still be reduced in that light bulb.
Yeah, the current will be going the same. Not only will it be reduced, it'll be going the same speed as the current going through every single resistor. And this is where I start to talk about those puzzles that we solve. Because the way I kind of look at these circuits when we're trying to figure out all of the voltages and currents and resistances and powers is, okay, how do we get to the goal of what we want based on the information we have? And sometimes you have to use certain principles to be like, okay, I know this, and because of this I can figure out this, and then I can use that to do that, and we'll get to it when we're actually talking like in a few more slides about a practical example. But that's the general idea. They are all going uniformly speed within a series circuit, and next week we'll talk about parallel. So over here in a single resistor, over in the top of this example here, we know that these three are in series with each other, And so the current going from the source voltage will be the same as the current going through the first resistor, same as the current going through the second resistor, same as the current going through the third resistor. And then the total current of everything, of the entire circuit, is going to be equal to the same one as each individual, right? Now think about that as a serious power mover for solving puzzles. Because all of a sudden, let's say we wanted to figure out the voltage of the third resistor, the voltage drop of the third resistor. Well, what we can do is we can find out, okay, I only have the voltage source. Pretend we don't have half the information down here. We have the resistance of each individual resistor. We know we can add together the resistance from each resistor to find the total resistance in the entire circuit. And then you can use the total resistance with the total voltage with to figure out what the current source would be, or the voltage source and the total resistance to figure out what the current of the entire circuit would be. So what we can do from that is we can say, okay, well, because we know the current of the entire circuit is the same as the current in each individual component, and we have the resistance of each individual component, now we can use Ohm's law again to solve for the voltage drop on A, the voltage drop on B, and the voltage drop on C. Does that make sense to all of you guys? Anyone have any questions? Cool. So let's keep on going. So we've talked about how we can add together all of the total resistances. Actually, I think this is doing pretty much what I just talked about. And then the current total is equal to the voltage source divided by R total. So we get the current to be 3.33 milliamps. And then because we know that there's 3.3 milliamps going through each of these, if we wanted to figure out the voltage at each resistor, we could just use Ohm's law. Now in this example here, we have, this is the same example as before, just what we're doing is we're solving for each voltage and each resistance individually. Sorry, we still don't solve for voltage. We're just proving that regardless of whether you do it using Ohm's law or whether you do it like just using the principle that each one's equal to each other, you're going to end up with the same current at every single step of the way. So if we looked at the voltage drop over here, we measure that it's like 9 volts, which will give us 2.7 kilo ohms of resistance with the 2.7 kilo ohms of resistance, which will give us the 3.33 milliamps. And it's like, I know it's less impressive when you see it on the board because you haven't taken those measurements. But remember, the current like autofills into everything. So you'll find practically when you go into the lab and you do these measurements, this is exactly how it works out. Like if you were to measure the resistance, the voltage drop over each of these resistors and measure the resistance so you know the exact resistance, you're going to end up with the same current on every single resistor within a series circuit. Okay. Now, what is the resistance of R3? We're gonna try doing this one together now. So let's see. Do you guys want me to draw this one on the board, or do you guys want to try knocking it out by yourselves? A little bit together? Okay. So you guys start. I'm going to start drawing it on the board. And then if one of you guys are super confident, you can come up or tell me what to draw. And we'll work through it together, okay? So you guys have like 2 minutes. Try to solve it. All right. Anyone get to the answer yet? How much more time do you guys think you need to figure it out? I see a bunch of people sitting and not doing anything. Yeah? 40 ohms. Oh, man. You could have told me this like 2 minutes ago. Yeah, I know, that's cool. Yeah. Okay, so let's just go over it then. Man, that sucks. Cool. So basically, one thing that we can do is we know that R1 is equal to, so the current of R1 is equal to 1 amp. So we can now know for sure the I of source is equal to I1, R1 is equal to I, R2 is equal to I, R3, which is equal to that 1 amp. So that's one property that we can like take advantage of, so we know all of those right off the bat. We already have the resistance for those guys, but we're trying to cut straight to the point, right? So what we'll do is, one way we can solve this is we can say, okay, well, I know V is equal to IR. So then R is equal to V over I, which is equal to 40 volts over 1 amp. And 1 volt per amp is equal to an ohm. So we get 40 ohms, which I think is the way they solved it there, right? Yeah. But how about we figure out the voltage source together? Yeah? So we have this one here, and we actually don't need this for figuring out the voltage source. What we need is we need to figure out the voltage for R1 and R2 and then add them all together, right? Yeah.
Wouldn't it just be 40? I mean, sorry,
80? I don't believe so, because if we add up, it would be 80 if R1 and R2 both together added up to 40 volts. But we see R3 already equals 40 ohms, and R1 and R2 don't add up to 40, so it'll be more than 40. Actually, you know what? We're going to figure out the total resistance since we already solved this. And then we can use Ohm's law. So resistance total is going to be equal to 40 ohms plus R1 and R2. So R1 plus R2, which is going to be equal to 40 plus 37.7, 40 ohms plus 37.7 ohms plus 23.3 ohms, 22.3 ohms, 2.3 ohms, which is going to be equal to, all right, so 3 is going to add up to there to make that 38 plus 2 is 40, 40 plus 20, yeah, exactly, 100 ohms, great, 100 ohms. And then if we use our RT to calculate voltage source, our voltage source is equal to, V is equal to IR, right? Yep. I source times, I total times R total, which is going to be our 1 amp times 100 ohms, and our voltage source will equal to 100 volts. Yep. Yeah? Cool. Awesome. So now we're starting to get into like low-level puzzles. Where did I put my clicker? Here we are. So now it wants the same voltage across R3, the same voltage drop across R3. So we know the voltage drop across R2 is 11 volts, and we have the resistance for each of these, and we have the voltage source is 80 volts. So what it goes ahead and tells us to do is let's figure out the current, because we know the voltage source of the voltage drop on B, and we have the resistance of B. We can use that to solve for the current total, because the current in each part is equal to the total current. And then from there, if we're looking for just this one and we have the current running through there, we can use Ohm's law again to solve for the voltage. So we're going to use, since we calculated already that the current is 5 milliamps, we'll use the 5 milliamps times the resistance of R3, which is 3.7 kilo ohms, and then that's going to give us our 18.5 volts. And then you could solve the rest of them as well. Option 2, it's saying, is you can go the other route and calculate the total voltage. So you can find the voltage drop in R1 and then use 80 volts minus both of these voltage drops to calculate R3 just by doing the subtraction of them from the source. Pretty straightforward? Cool. Oh, excuse me. So here we want to know what the voltage source is. And so what we're given is the power of the motor. We're given the resistance of R1, and we're given the total current. So what we're going to do in this case is we're going to go ahead and use our other equation for power, our power from our power wheel that we were using the other day. And we're gonna use that to calculate the voltage drop going through the motor. Once we have the voltage drop through the motor, we can calculate using the current. And so current and power is gonna give us our voltage for the motor. Then current and resistance will give us the voltage for our resistor. We add them up and we end up with our voltage source. So voltage of the motor is equal to this one was the VIP one. VI is equal to P, right? So we rearrange that to say voltage is equal to P over I, which is gonna be the 10 watts over 2 amps, which will give us 5 volts. And then for resistor 1, we have the 2 amps times the 2.5 ohms, which will give us 5 volts as well, which means we add up the 2 of them and we end up with our 10 volts for the voltage source. That's also a little bit straightforward, right? Just now we're dealing with power as well. But it's all just a formula that you guys have on that power wheel, right? Mm-hmm. Cool. Now this time we're gonna use power. So instead of having, sorry, what was our explanation? Okay. So now instead of having the current, we're gonna have the power on R1, and we're gonna have R1, and then we're gonna have the power of the motor. So from here, who can, without looking at the solution, tell me what method they can use to get the same voltage source through this means? You're just trying to hypothesize what pieces you have to use in what order to get to the solution, right? Don't give me the answer. I just want someone to throw out their thoughts. Take it like throwing dirt at the wall and seeing what sticks. Someone raise up their hand. Don't make me pick someone, guys. Pick. Okay. You.
You divide the power by the resistance.
You don't even have to go that far. You can just say we're going to figure out the current using the power and the resistance from the resistor 1. Yeah? So that's your first step, right?
Yeah.
And then what?
And then square root it.
Square root it. I'll come back. Okay, I'll explain in a minute.
So you have to just divide the power by the resistance, and then you get its current.
Yeah. So, okay, I'll take over, guys. Essentially, you can use power and resistance to figure out the current, right? Because we have a formula for that. V is equal to IP. So we have a relationship between current, power, and voltage. Once we figure out the current for this guy, sorry, there's a step in between there. We actually need to use 2 formulas to figure that out. Let's just do it, okay? All right. So I'll show you guys where I misspoke and then how we can get to the solution either way. So I said we have V, I is equal to P. What that doesn't do is that doesn't relate it to resistance, right? So how do we relate it to resistance? Can someone remind me of Ohm's law? Everyone together, what's Ohm's law? V is equal to IR, exactly. And because we want to know about resistance, we need to have resistance somewhere in here. Now, what are we ignoring? We have power, so we have power is equal to 10 watts, and we have resistance. Resistance is equal to 2.5 ohms. And we're looking for voltage. Voltage equals, we're looking for current, right? Because then we can solve everything within there. So current is equal to question mark. I is equal to question mark. So what we want to do is we want to get rid of voltage, because the voltage isn't going to help us right now, funny enough, because we're looking for the current, because the current is what's going to give us the current for the entire circuit. So what we do is we say, okay, let's isolate voltage, and then substitute voltage into the other side, into the other equation. So I is equal to, sorry, we already have it for this one, okay? So we're just gonna pop this in for voltage. So we're gonna have IR times I is equal to P. So I squared, oh, you know what? You said we're gonna take the square root, and we are gonna take the square root. That's funny. Not funny. You knew what you were talking about, and I didn't. Cool. So I squared R is equal to P. And then we're solving for I, so we move R to the other side. So I is equal to P over R, and we take the square root of both sides. So it's gonna be the square root of P over R. Yeah? And I don't know if this is totally the way that we're solving it here. Cool. So from there, we have our data. We can go ahead and just be like, okay, that's equal to the square root of 10 over 2.5. What does that give me?
2.
2? Really? Straight up 2?
Yep.
Because 10 times
10 over 2.5.
10 divided by 2.5 is 4, and the square root of 4 is 2. Interesting. 2 amps.
Exactly.
All right. And that's going to be the current for everything. And then from there, it's smooth sailing, because we can calculate the voltage from that with the current. We can calculate the voltage now for the motor with the current, because we have this beautiful formula here. So voltage is equal to power over current, right? And we just pop it in. We get our answers. We add them together, and we end up with the voltage source. So we got that far. Then we just plug in straight 10 watts, which is going to be the power for the motor. Multiplied by the 2 amps squared is going to equal to 2.5 ohms. And then 2.5 ohms, sorry, we don't need to do this. We could figure it out with just, yeah, with just this, right? So let's do it the other way, because I don't like this way. Cool. So from here we have for the first resistor 1, and that we're looking for the voltage. So voltage 1, R1 is equal to IR, so I times R1, which is going to equal to 2 amps times the resistance is 2.5 ohms, 2.5 ohms, which is going to be equal to 5 volts, VR1. And then we can use for the motor this formula over here. So V is equal to power of motor divided by the current, which is going to be of the motor, which is equal to those 2 amps, which is going to equal 10 watts divided by 2 amps, which is equal to 5 volts. And then volt total is going to equal to voltage of the drop of resistor 1 plus the voltage drop of the motor, which is equal to 5 volts plus 5 volts, which is equal to 10 volts. It gets either the same way. Yep.
I'm a bit confused on why we're going to do a square root on the root.
Sure. I can go through that again for sure.
If that's okay.
So you remember these two formulas here? I'm going to erase it and just get back to there, okay? Can you see the side of the board well?
Yeah, it's just glaring a bit.
Here.
But it's okay. I can just leave it over.
Is that a little bit better?
Yeah, thank you.
All right. So we have two formulas that's going to help us, right? And it's always super important whenever you're like trying to figure out what formula to use to start off with what you have. So we said that we have our formula V is equal to IR, which is Ohm's law, and our power law is VI is equal to P, or VIP is the easy way for me to remember it. Now we have power, because we're just looking at the first resistor right now, right? So we have the power, we have the resistance, and we're looking for current this time. Because using the currents principle, we know that the current at the voltage source, we'll know the current at resistor 1, we'll know the current at the motor. So,
It's just series, right?
yeah, because it's in series, so it's equal all over.
Yeah.
So the most useful piece of information we can get right now is that current. So power is going to be equal to our 10 watts at relay 1, so resistor 1. And then over there it says resistor 1's resistance is equal to 2.5 ohms. Okay, and we said we're looking for the current. So because we're looking for the current, what we want to do is we want to isolate voltage so that we can get rid of it in the second equation, right? Because we need to make a relationship between power, resistance, and current. There's no voltage there, right? And if we have two unknowns, we can't solve, but if we have one unknown, we can. So, well, we can if we have multiple equations, but let's not get complicated, you know? Keep it simple. So what we're going to do is we already have voltage isolated here. We're going to plug this into the voltage here, right? So instead of it being V, it's going to be IR, because we know IR is equal to V, times I is equal to P, right? So that's going to give us, because these are multiplied, I squared R is equal to P. But then what are we looking for? We're looking for this one. This current is what we don't have, right? So what we do is we transfer we divide both sides by the resistance. So divide by R divided by R. These two cancel out to 1. And then how do we get rid of the square on I squared?
So you have to square root.
You have to take the square root. So you take the square root of power over resistance. Does that make a lot of sense?
Yeah, thank you.
Okay, great. So let's move on. Did I go too far back? Yeah, okay. So now about voltage sources and stuff like that. We have a similar situation here where you can get the total power, like the voltage source, by adding up all of the cells that are in the same orientation, if that makes sense. So if you have like, are you guys good with this? I can erase this? Yeah, yeah. 2 seconds and then we'll move on. Or you can take a picture if you want. I'll get a nice sip of coffee. All right, you good? Okay. So if we have a bunch of cells, so here in the picture, there's 3 battery cells, right?
Yeah.
So we're gonna add these like this, right? So short to long, short to long, short to long. This is the negative side, this is the positive side, negative side, positive side, negative side, positive side, and they're all connected in series. So what it's saying here is because each one of these are 1.5 volts, 1.5 volts, 1.5 volts, the entire power drop, or power lack of a drop, I guess, the actual power, or your voltage source is going to be this, which is going to be 4.5 volts. Yeah, Andrew.
So what happens if you have this system, but in parallel? And like,
I think you just have parallel. I don't think they add up like this or anything like that. Usually when people put batteries into parallels because they want a longer battery life. Does that make sense? Now there are times when you'll need different voltage levels as well, but that's all again kind of separate conversations. The main thing you would use parallel batteries for is for extending battery life. Now here's the question that we're going to get to pretty soon, but I'm just doing it before the slides. If we were to flip this one over here so that the positive is on this side and the negative is on this side, do we still add it? What do we do with it? Subtract it. Exactly. So if it was like this, then we subtract that one because it's confronting the other ones. It's pushing the electricity in the opposite direction. So instead of it being 4.5, it will be back to 1.5. Yeah? Okay, we'll get to that in a minute. So it's kind of showing us here, no matter the shape here, when you're going through one after the other, the only thing you have to pay attention to is the same side, the side closer to, let's say this is A and this side's B. Is the side closer to A always long? If not, you have to subtract, right? So this one's the long side, 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 and V7's the long side. So we would add all of the voltages together until we get our, what do we call it? Honestly, until we get our voltage source total. Oh, VST, voltage source total. Cool. Okay. And then we did the math already for this. And this is what we just said as well. Does anyone want to give me the math if all voltage sources are 10 volts? 70, because there's 7 of them. 7 times 10 is 70. Exactly. Oh, Josh, you caught us. Which one was the opposite direction?
Well, V1 and V6.
V1 and V6. Yeah, so 2 of them are in the other direction. So it not only doesn't add, it literally subtracts. So we have 5 times 50 minus 2 times 20, right? Which is going to end up with our 30. Someone had a question? No one had a question? Okay, cool. Now the total power in a circuit that's series, it works the same way as resistance. We just add them all up. So now we have a new property we can use to figure out things, right? So in this circuit over here, if we wanted to know the power of the motor, and we know the total power is 20 watts, the power of resistor 1 is 10 watts, based on what we just discussed, what's the power of the motor?
10 watts.
10 watts, because 20 minus 10 is 10. Yeah, exactly. And then from there, we can just go ahead and solve for current and voltage. You guys know how to do that already. And yeah, there's step-by-step instructions for the rest of this if you guys want to go through it. I think you guys are good at this point. Maybe we'll do 1 or 2 more examples if need be. And then one other thing that we need to get to is what happens if there's an open circuit. So the start of the circuit and then somewhere in the middle of the circuit, anywhere in the circuit, has a full disconnect, like the 2 sides just aren't connected. Well, then everything in the circuit has a 0 voltage drop. Now, one way you could look at that is this is, let's say, 30 volts. On this side and this side of the resistor, there's both 30 volts. So technically, it doesn't move. There's no change in voltage. So it has a voltage drop of 0. And it's the voltage drop that causes the flow of electrons. And then on the other side here, resistor 2 has 0 volts and 0 volts on both sides. So it has a 0 voltage drop because 0 minus 0, same as 30 minus 30 is 0. And then therefore, if the voltage is 0, the current is 0, regardless of the resistance, because V is equal to IR. So if V is equal to 0, the resistance is equal to whatever number. The only thing that's left is the current to be equal to 0, because resistance is measurable, regardless of the current flowing through it. And so it's going to tell us from this opening to this opening that this side has 30 volts, this side has 0 volts, even though there isn't current flowing through it. The drop is 30 volts because the left side has 30 volts and the right side has 0 volts. Does that make sense? Anyone confused? Yeah, we're good? Or you have a question? No? Okay. So what we did in lab 1 is we used a wire to bypass one of the what's it called? One of the resistors, exactly. So if we had a 500 milliamp fuse, over here you see this squiggly line, kind of like a wave. That's going to be the symbol for a fuse, and it says it's 500 milliamps, which means if the current goes above 500 milliamps, it's going to pop. Exactly, and then you'll have to replace the fuse. So if we have originally 120 ohms of total resistance, and then we short 100 ohms of that 120, will it be above or below 500 milliamps? Will that fuse pop? Without looking at all of the answers, anyone want to try it out? You guys want to solve this one together? Yeah, let's do it. Does everyone want like a 2-minute body break to just shake out, or do you want to do it between the PowerPoints?
So I feel like you're just kind of moving too fast. That like I can't even write the formulas down.
Tell me to slow down. I'm happy to slow down, 100%. So where do you need me to go back to if you feel like I've
Well,
gone
this
too far?
right, like I've just missed so much. I'm just gonna go back on my own time. Like it's not even worth it.
Yeah, sure. But I feel like if you're feeling like I've been going too fast, everyone might be feeling like I'm going too fast. Does everyone feel that way? Put your hand up if you feel like I'm going too fast. I only give praise to people who call me out on my stuff. And you guys know that because I've never once given anything but compliments to someone for calling me out. A little bit?
Yeah, in some things,
Yeah? Please, please, please slow me down. Tell me, hey, I don't understand this. Can you go over that one more time? Like, I'll slow down. I want you guys to learn as much as possible. So, for sure, let's do that, okay? Which areas did you guys really understand? Do you guys understand adding up resistance in a circuit? Kind of? Maybe a little bit yes, a little bit no? Okay, let's retract that over again. So the total resistance in a circuit, resistance total, you just add up the resistance of each part. So no matter how many components you have in a series circuit, if you take the resistance of each of them and add them together, just add regularly, if you have all of the components, you'll have the full resistance total for series. Therefore, if you have the resistance total and you have everything except for one part's resistance, you can subtract everything from the resistance total to get that one part. So let's say there's 3 resistors, right? So resistance total will be equal to resistor 1 plus resistance of 2 plus resistance of resistor 3. And let's say we're looking for resistance of resistor 2, then resistor 2 would be equal to the resistance total, and then we just throw these over to the other side of the equation. Resistance total minus resistance 1 minus resistance 3. Does that make more sense? Yeah? Okay. Now it's the exact same thing for power. We can just substitute the R for a P. So power total is equal to, assuming there's 3 components, power of 1 plus power of 2 plus power of 3. If they're resistors, we would usually put like R1, R2, and if the third one's a motor, we would probably put like M for motor. And then if we wanted to figure out the power of the motor, and we had the power total and the resistance and the power of both the resistors, we could just say power motor, and we throw these 2 over, is equal to power total minus power of resistor 1 minus power of resistor 2. Does that also make equal sense? And then I think personally the easiest one is current, because current is just the same everywhere.
Our total, like the first one, is equal to R1 and 2 and 3 or plus? The first equation.
So this one, the R, sorry. Thank you. So current is equal to, total is equal to current of 1 is equal to current of 2 is equal to current of 3 forever. Those are like the main formulas you need, right? Everything pretty standard so far. I think the only other thing we really went over is in a battery, so voltage source total is equal to the sum of all of the voltage sources in the same direction. So if it's backwards, we'll call it negative. If it's forwards, we'll call it positive. And then we can just say voltage source 1 plus voltage source 2 plus voltage source 3. Okay, is that pretty comprehensive of everything we've done up to now? Is like a decent summary? Yeah? Is that slow enough for you guys? Be honest with me, okay? Okay, cool. So let's take a look at this on the board now. So we have the voltage source, which is 12 volts, and we're going through a fuse that will pop off when it gets to 500 milliamps. And then we have resistor 1 at 10 ohms. R1, 10 ohms. Resistor 2 at 100 ohms. And resistor 3 also at 10 ohms. Okay? So the question is, if we short from here to here, will this fuse blow? Man, you guys are so much faster than me now. No, I'm joking. So let's just take a quick look. Before we blow the fuse, we said the voltage source is 12 volts, and the total resistance would be, so resistance total would equal to resistance 1 plus resistance 2 plus resistance 3, which is going to be 120 ohms, right? 10, 100, 10. So 120 ohms. And therefore the current, so we said if V is equal to IR, I is equal to V over R. So I is equal to voltage source over resistance total. And the thing to notice is these symbols are always matching. Current total, voltage source, resistance total. If we were talking about the first resistor, we would have current at the first resistor, voltage of resistor 1, resistance of resistor 1, right? They always have to be about the same scope. So if we're looking at one component, everything has to be about that component. If we're looking at the entire circuit, then everything that we're doing math with has to be about the entire circuit, right? So we have the voltage source, we said is 12 volts over 120 ohms. And that's going to equal 0.1 amps, so 100 milliamps.
Yep.
100 milliamps. As soon as we say we're going to skip over this, right? So the alternate reality would be minus 100 ohms, because instead of it going through all three resistors, electricity follows the path of least resistance. AKA, like engineers, electricity, if it doesn't have to do work, won't. So instead of going through all three of them, it'll come around this way, and we'll only be going through this 10 and this 10. And the minute amount of resistance within the wire itself, but especially for calculations, we assume it's a perfect world, and there's no resistance in the wire. Yeah, Andrew?
So does that mean there's absolutely no current going through that bypass?
100%. Zero resistance is going through resistor 2. All of the current is going straight through the bypass of wire.
So technically I could, I'm not going to do this. I could stick a fork in the outlet. But if I'm wearing, like, I don't know, some crazy, like, rubber gloves, then I won't be fine.
Yeah, so the situation where a person has a glove that can handle the amount of calorie damage from an electric burn that would come from sticking your fork in a 120 volt outlet AC, you would technically be okay. But remember what happens when you short circuit an entire system. So we're really calling this a bypass. I use the word short, we use the word short, but it's not a proper term. Because properly, if you were to short a circuit, it's really going from voltage source to voltage source, you know, from 12 volt to 0 volt. That would be a full short. And what's the problem with that? Well, we know that the current is equal to the voltage divided by the resistance. So if we were to say we have voltage, the voltage is something, but we're making this resistance very, very, very close to zero. What's going to happen to the current? Well, we said in our previous lesson, current is inversely proportional to resistance. So as the resistance goes down, the current goes up. And how many pieces, if you were to take a cookie and break it in half until each piece of the cookie was zero big, how many pieces of cookie would you have? You would have an infinite number of cookie pieces or crumbs. Crumbs is putting it generously. So what we're doing by this is really we're causing the current to skyrocket to infinity, in a sense. Now, the other problem with that is there are certain ratings. There's a certain amount of current before there's a meltdown or a breakdown of the material that's handling that current, right? So if you start shoving practically infinite current through a device or a wire, it's going to start having a lot more friction. You can imagine, you don't need, if you guys take your hands and you start to rub them together, right? Your hands start to get warm really quickly. Now do that faster and faster. The faster you do it, the hotter your hands are going to get. So you have that happening on an electron scale with the wire approaching infinity, and the wires start getting really hot. So hot that they can in fact melt, or really quickly melt, or if there's something that has like electrolytic fluid inside of it, like a capacitor, then that might just like explode, whatever the case is. So it's very dangerous to do, even if you might be okay from the outside. And then all of the components leading back might also have a problem.
So you could say that, like, because there's I don't know how many meters of air between me and that outlet. There's no current flowing between me and that outlet.
Do you feel the current from that outlet?
Well, it could be super small. I don't know.
Yeah, it's a really good question. I would say the inductive quality of air is absolutely enormous. You need like 3,000 volts for electricity to travel just like an inch through air, which is why for like lightning and stuff, you have millions upon millions of volts, and they're still jumping between all of the raindrops to be able to escape all the way down to ground from the clouds. So, excuse me, I don't think any of the voltage from there is hitting you. What might be happening is all of the wires create like some magnetic field, and those magnetic fields might be interacting with your body in some way, shape, or form. But that's, again, way beyond the scope of this course. You had a question?
I was just gonna say, isn't a good example for that a heater? Because when you put the voltage like through this resistor, will make a heat, right? So.
Yeah, so that's one way to make a heater. The better way to do it is they have very specific substances that they realized produce a lot of heat when electricity goes through them. Now it does take like a large amount of voltage consumption usually, and there's more efficient and less efficient ones. But they're called, there's a whole category called transducers. What a transducer does is it takes electricity and converts it into another form of energy. So we can take the electrical energy and convert it into heat energy, right? A resistor technically does take electricity and convert a small portion of it into radiant heat, but it's not its purpose. Its purpose is really, they try to make the heat that comes off of it minimized, and it's just to try and slow down those electrons. Very specifically engineered materials.
Shorting R2, how does the current still get to R2? Or
Yeah, so that's exactly it. So instead of it going straight through each resistor, it comes this way, and then it says, oh, there's an easy pathway, I'm just gonna go this way instead of going through the resistor. Yeah, it's like, I don't wanna push that 100 ohms, it's too heavy.
Based off what Andrew was saying, like how things travel through the air with voltage, is that kind of like how those Tesla coils would work?
Yeah, so short version to your answer is, did we talk about transformers at all? All right, so short version of transformers, I know we haven't, like, we're just talking about series circuits, and transformers are like a whole thing on their own. But the short version is, a transformer takes a small number of coils and a larger number of coils, and it converts from low voltage to high voltage. At the same time the voltage goes up, the current goes down. So what Tesla did was he said, okay, I can take, I don't know if this was the exact thoughts going through his head, but basically it turns out that this device takes a small number of coils, of turns, converts it to a much larger number of turns, which then has the ability to stretch out, but the current doesn't necessarily have the same, the current does drop when that happens. And that's kind of where you have the Tesla coil. So you've noticed like people even like touch the plasma coming off of them once they're close enough, and it doesn't actually hurt them most of the time, unless it's like high voltage ones, which are made like seriously. And that's because the current is very low. Current is what kills people usually, not the voltage. Yeah, exactly, current. So back to the question here. So now we have 20 ohms here instead of this 120 ohms. So everything up to this point is copied, but this turns to 0. And so we have current total is equal to voltage source over resistance total, which is going to be equal to 12 volts over 20 ohms. And that's going to give us 0.6, because 12 divided by 2 is 6, amps, which is really 600 milliamps. And 600 milliamps is over 500 milliamps. Therefore, because 600 milliamps is greater than 500 milliamps, the fuse will blow. All right. We all on the same page so far? Cool. You guys promise you're going to slow me down, right? Okay, cool. So this is kind of what it's showing us before the short, after the short, which is what we just calculated. Before the short, the current was going through all of these components, which means there was 100 ohms worth of resistance for the 100 volt source. And then when we shorted from here to here, now there's only 18 and 10 volts, which is 20 ohms, which is 28 ohms, which is going to give us 3.57 amp for the entire circuit instead of the 1 amp for the entire circuit. And you can see how we were talking before. The current that's going through all of these unifies itself. It's the same current. It's the same current. It just all slowed down, or it all sped up. It just doesn't have middle grounds. Okay? And like one way that might make it a little bit easier to visualize is, you guys ever take two magnets and you try to like put the same pole together, like north to north, and they repel each other? So what's actually moving around is the electrons, and the electrons have kind of like a negative force around them. So negative to negative also repels. And so it spaces itself out evenly through everything, even though each portion has a different amount of resistance through it. As the electrons are trying to go together in a unified path, they all follow more or less the same speed, because they're all spacing each other out as they're going through them. Andrew?
So doesn't that mean like a permanent magnet has like unlimited power, because there's electrons kind of there?
Your power is a very specific term.
Or like, I don't know, energy or something?
Energy is also a very specific term. I know what you're saying, and you're not wrong in your intention, but based on the very specific language that we use to define energy and power, it doesn't quite work. let me give you an example. Like, let's say you generate an electromagnetic field in a coil, right? If you're using DC current, as soon as it reaches its full magnetic field, so the electricity is going to come into the coil and it's going to start to build up its electromagnetic field. As soon as you let go of that field and the electricity, it's going to take that field and put it back into the coil as electrons moving. Now the same token, once it fills up, it no longer has its voltage drop. So you have a voltage drop as it's filling up its magnetic field. Once it's filled, it kind of acts like a buffer.
So it's kind of like a capacitor.
They work like a capacitor. The only difference, and again, this is a Mechatronics 2 conversation, is they're perpendicular to how resistance works. So one's called, one's measured in henries and the other one's measured in capacitance.
Yeah.
So they kind of go like this way and that way. They're opposite from each other and they cancel each other out. So if you had the same amount of inductance as you did capacitance, inductance is henries, so coils, capacitance is capacitors and farads. So if you had the same amount, they would cancel each other out. And one of the things you try to aim to do and this is again talking about AC currents, not AC circuits, not DC circuits, which is a different conversation as well. But you want to have things kind of like, you want to minimize we call it kind of like it's almost like a phase shift, because so you pulled out a word a while ago called impedance, and impedance is equal to the square root of the resistance plus either the inductance or the capacitance, depending on which one outweighs the other, and you add them together the same way that you use Pythagorean theorem. It's the square root of like a squared plus b squared, right? Because you're really creating a triangle, and it's the angle on the triangle that creates your impedance. And so if you want to have a more efficient circuit, generally you want to try to get that impedance as close to resistance as possible so that you don't have like a burn on electricity. But you need the capacitors or inductors to do specific jobs. So like again, it's way beyond this course, but I don't want to leave you hanging either, right? Okay. Anyone have a question related to shorting? Yeah? Oh no, you're good.
Actually, I do have a question.
Okay.
So, if you short, let's say 1 volt to the 1 volt, the current is 1 amp.
What do you mean 1 volt to 1 volt?
So, sorry, let's take this example for a second. If you take that 100 volts and then add a wire directly to the positive terminal.
So you're saying just
is
short.
the amperage just like infinite? Like what?
Yeah. If you were to go from this side of the power supply to the other side of the power supply,
It's infinite.
because the wire's resistance is so low, it's like very close to zero.
So, okay, I know. Let me just get this out. So, if that's true, and there's tons of current flowing through that new wire, and the wire melts and whatever, and it turns to plasma, what, like, would that kind of cause? Would that? How do I say this? Would that induce the current in the rest of the? Because there's just so much.
Okay, so what you need to know about is something called flux. So for electromagnetics, and again, I don't think you're going to learn this in this course, but essentially, like the entire 3 years, I don't think you guys will learn this. But basically, there's something called flux when it comes to magnetic fields. So if I have a north magnet kind of facing that way, and I have a coil that I want to induce a current into, the amount of current induced is, let's just use the word proportional to the flux angle of it. So if you have the magnetic field directly facing the coils, that's when you're going to have a transfer of the, and it's better to use electromagnetics for the example, because the magnetic field would have to be like moving for it to have a changing magnetic field to generate the electrons to move in the coil. But if you had it like in parallel to the coil, then it won't create any, because the flux angle would be 0 and cos 0 is 0. Was it sine 0 or cos 0? That I'm a little bit rough on. But essentially, with this situation, you just have a battery and one straight wire. You're not inducing current really into anything next to it. It's a form factor thing, and direction, and then you have proximity. There's a lot of different factors that go into it, but the short answer is no. Okay, so that's it for this PowerPoint. I'm gonna let you guys shake out after this, and then we'll just do a quick PowerPoint on voltage dividers, and we'll be done for today, okay? I'll let you guys go over the summary by yourself, because honestly, I don't really like reading for, like, just recapping this stuff. Okay?